knows a lot about the science stuff. Professor Dave explains.
Now that we've discussed the building blocks of the Standard Model, and discussed physical quantities that can be measured to describe interactions between the components of the model, it's time to investigate some of the equations that actually make up the model and dictate how it behaves. Hundreds of years of classical mechanics were built on Galilean invariance, which dictated that physics needed to be the same for any inertial reference frame. This facilitated a lot of the early work done by Galileo and others, and it helped Newton develop his theory of gravity, which was the dominant paradigm until Einstein. Essentially, the math was developed so that one person wouldn't observe different physics than another. However, as Einstein realized, this framework breaks down at extremely high speeds, where special relativity then dictates the laws of physics. The foundational principle of special relativity is the invariance of the spacetime interval, which was defined by Einstein as ds squared equals negative c squared dt squared plus dx squared plus dy squared plus dz squared under Lorentz transformations, as well as the universal cosmic speed limit set by the speed of light c. Note that dt, dx, dy, and dz are coordinate differences. Check the 4-part mini-series on special relativity from earlier in this playlist to review. The signs in this spacetime interval are dictated by something called a metric, which describes the nature of spacetime. The metric can be written as something called a tensor, and is an important component of general relativity. We will come back to general relativity in more depth after we're done with particle physics. However, we can safely conclude that due to all these relativistic complications, it is not easy to apply classical motion equations to things like particles. Even though they often have mass and cannot travel at the speed of light, they still move at extremely fast and often relativistic speeds. Quantum mechanics was developed around the same time as relativity, but did not incorporate any relativistic ideas into the original Schrödinger equation, since it is not invariant under Lorentz transformations. To describe relativistic particles in quantum mechanics, a wave equation must respect this symmetry. As a result, the Standard Model required a relativistic wave equation that was still consistent with recently developed quantum mechanics. To continue with this topic, we must be aware of what a tensor is, since tensor notation is frequently used. A tensor is sort of like a vector, but more general, in that it is a generalization of scalars, vectors, and matrices that can apply to any number of dimensions. It represents an array of components that are functions of the coordinates of a space. So it describes a multilinear relationship between sets of algebraic objects associated with a vector space. We will examine tensors in more depth when we investigate general relativity, but for now we can simply be roughly aware of the definition and what the notation looks like. We will use this notation fairly minimally for the time being, along with Einstein's summation notation, which is used for implicit summation in the following manner, where this equation would indicate the sum over the index nu of x upper index nu times x lower index nu can also be written as x upper index nu times x lower index nu. The first attempt to formulate a relativistic version of the quantum wave equation led to the Klein-Gordon equation, which can be written as 1 over the speed of light squared times the second time derivative minus the Laplacian operator plus m squared c squared over h bar squared, all multiplied by psi, the wave function, equals 0. From now on, we can define 1 over the speed of light squared times the second time derivative minus the Laplacian operator as the D'Alembert operator, represented by this box symbol. This equation is derived by applying the energy-momentum relation from special relativity, which is Lorentz invariant. Energy E squared equals c squared p squared plus m squared c to the fourth. Using the so-called quantum prescription, we can modify energy to I times h bar times the partial derivative with respect to time, and we can modify momentum to negative I times h bar times the gradient operator. This changes the scalar values of energy E and momentum P into quantum mechanical operators that are algebraically compatible with the rest of the hidden linear algebra in these expressions. Additionally, factors of I times h bar are added to adapt the values to the quantum scale. This is a similar approach to the original Schrödinger equation, which can be derived from applying the same quantum prescription to the standard conservation of energy equation, p squared over 2 times mass mass plus potential V equals energy, and multiplying by a wave function psi, which gives negative h bar squared over 2m times the Laplacian of psi plus V times psi equals I h bar times the first time derivative of psi. Unfortunately, the Klein-Gordon equation was not a successful generalization of the Schrödinger equation, including relativity. It fails to reproduce the energy levels of hydrogen. However, it was later realized that in the context of quantum field theory, this equation could be useful. The Klein-Gordon equation successfully describes scalar or spin-zero particles and is Lorentz invariant. However, it suffers from a major issue. The probability density is not positive definite. This means solutions to this equation can lead to negative probabilities, which are not physically meaningful. As applied to quantum field theory, this density is interpreted as a charge density, which allows for negative values. However, the standard model still needed an equation that could describe spin 1/2 particles, allowing it to model leptons and quarks. To address this, Paul Dirac proposed an alternative wave equation to overcome the deficiencies of the Klein-Gordon equation. His aim was to find a first-order differential equation in both time and space derivatives, which should solve the problem of negative probabilities and provide relativistic quantum mechanics because of the close relationship between space and time in the context of relativity. The Dirac equation is, in tensor notation, in parentheses, I h bar gamma upper index mu times the 4 gradient, written as partial with respect to mu, minus mass times the speed of light, all times psi equals 0. Gamma mu are 4x4 matrices that satisfy a special relationship involving the metric tensor of general relativity. Additionally, the 4 gradient is a derivative of both time and space. Notice the upper and lower indices implying a summation. Interestingly, the psi in this equation is a 4-component object called a spinor, rather than just a scalar wave function as it would be in non-relativistic quantum mechanics. These spinors encode information about the spin dynamics of the particle, and a general spinor can be written as shown here, similarly to a vector with 4 entries. The components of the spinor encode information about the spin degrees of freedom for these particles as they interact with the world around them. Since the spinor is defined at each point in spacetime, it represents a field, rather than a particle wave function or specific quantum state, as psi does in traditional quantum mechanics. This is true for the quantum field theory interpretation of both the Dirac equation and the Klein-Gordon equation, which, as the QFT name suggests, corresponds to a shift in understanding from focusing on quantum states to quantum fields. Now let's imagine the Dirac equation for a particle at rest. In this scenario, the solutions to the equation will look like this. Psi a of t equals e to the negative I times t times mc squared over h bar times psi a at time 0. And psi b of t equals e to the positive I times t times mc squared over h bar times psi b at time 0. Here, psi a and psi b at time 0 are time-independent spinors. This can be easily obtained from setting mu equal to 0 in the Dirac equation, since the spatial derivative of psi is 0 for a stationary particle, and plugging in the gamma 0 matrix. From our study of quantum mechanics, we should be able to recognize the e to the plus or minus I times t times e over h bar factor in both equations. However, something interesting has happened. The solutions imply that one particle has e equal to m times c squared as expected, but the other has e equal to negative mc squared. How could this be possible? A negative energy? This represents the solution for an antiparticle. For example, psi a can represent an electron, while psi b can represent a positron. This implies that the existence of antiparticles naturally emerges from the Dirac equation. Each of these are 2-component spinors, representing half of the total 4-component spinor. The 2-component spinors represent a spin-up and spin-down state. This can also be done for a generalized momentum, where we find that k mu equals plus or minus p mu over h bar, representing the momentum of particles and antiparticles. By convention, particles, symbolized by the letter u, and antiparticles, symbolized by the letter v, have states written generally as psi being equal to some amplitude a times e to the negative I times p dot x over h bar, all times u for particles, and psi being equal to some amplitude amplitude A times e to the positive I times p dot x over h bar, all times v for antiparticles. These are the solutions to two corresponding separate Dirac equations, gamma mu times p mu minus mc all times u equals 0 for particles, and gamma mu times p mu plus mc all times v equals 0 for antiparticles. These equations and the spinors that are their solutions are able to provide a relativistic and quantum description of spin 1/2 particles. Additionally, as we said, it predicts the existence of antiparticles. This prediction was experimentally confirmed with the discovery of the positron by Carl Anderson in 1932. In the Standard Model, antiparticles are fundamental counterparts to particles and are integral to particle physics phenomena, such as annihilation and pair production. Spin is another essential characteristic. It is an intrinsic form of angular momentum carried by elementary particles that cannot be explained by classical rotation. For elementary particles, spin is quantized and takes specific values. As we mentioned, fermions have half-integer spins, while bosons have integer spins. This quantum property gives rise to magnetic moments and plays a crucial role in atomic structure and particle interactions. It is also conveniently contained in the Dirac equation, the relativistic generalization of the non-relativistic Pauli spin matrices are the gamma mu matrices that appear explicitly in the Dirac equation. Helicity, on the other hand, is the projection of a particle's spin onto its momentum, or h equals the spin vector s, dotted with the momentum vector p over the magnitude of the p vector. A particle has right-handed helicity when its spin aligns with its momentum, and left-handed helicity when they point in opposite directions. For massive particles, the helicity depends on the reference frame of the observer. If the observer is traveling faster than the particle, they should see the momentum flip signs while the spin remains the same, which results in a flip of the helicity sign. For massless particles, helicity is independent of the reference frame because the particles are traveling at the speed of light c. In this case, helicity is equivalent to chirality. Chirality is a more abstract concept related to certain types of transformations, and which plays a crucial role in the Standard Model, as weak interactions couple only to left-handed particles and right-handed antiparticles. This asymmetry is built into the math, and leads to some interesting questions involving weakly interacting particles like neutrinos and their potential Majorana nature, meaning they could be their own antiparticle. Antiparticles have the same spin as their counterparts, but they have opposite charge and helicity or chirality. Now let's discuss the way these equations can be diagrammed. Feynman diagrams are visual representations used by particle physicists to describe the interactions of particles. They serve as a crucial tool for simplifying and organizing the calculations required to predict physical processes involving particle interactions. The diagrams depict particle interactions as lines and vertices. Straight lines represent particles like fermions, while wavy or dashed lines often represent force-carrying particles, such as photons or gluons. Three key components of Feynman diagrams are external lines for incoming and outgoing particles, internal lines for propagators, and vertices representing interaction points. In addition to visual components, each element of a Feynman diagram corresponds to a mathematical term in the calculation of an interaction probability. Often, interactions in the Standard Model must be described using perturbation theory. Since there are not many problems in physics that we can solve completely and exactly by hand, perturbations allow us to modify a simple approximation of a system that can be solved to make the approximation look more like the real system. This approach can only be used when the interaction strength is small, because it requires using different Taylor approximations. This means that if we define a coupling constant A, which is proportional to interaction strength, it must also be small. Using perturbation theory to solve problems involves expanding the solution to a physical problem in powers of the coupling constant. Each term corresponds to a specific interaction order. The lowest order interaction A0 often represents the simplest version of the problem, with higher order corrections represented by A1, A2, and so forth. These each represent increasingly complex interactions that can all be visualized with Feynman diagrams. Each of these diagrams contributes a mathematical expression to the overall probability probability amplitude of a process. To find the total probability, all possible diagrams are combined. Similarly to combining the decay rate and branching ratio from multiple decay pathways, as we discussed earlier. Propagators describe the probability amplitude for a particle to travel between two spacetime points. Different types of particles have different propagators associated with them, which are incorporated as factors multiplied into a calculation from a Feynman diagram. Here are the propagators for different types of particles, those being spin 0, spin 1/2, spin 1 massless, and spin 1 massive. With these, g mu nu is the spacetime metric from general relativity, and q mu is the momentum 4-vector. These propagators allow for systematic computation of amplitudes for complex processes. For now, these propagators give you an idea of what the terms can look like in calculations. With these first few tutorials, we have completed an introduction to the Standard Model, decay rates, and cross-sections. We've introduced the particles and interactions that make up the Standard Model, and explained some of the equations that pertain to these interactions. We've introduced the idea of Feynman diagrams as a way of tying all of these concepts together into a visual representation that also serves as a valuable calculation tool. In the next few tutorials, we will start to explore the forces and symmetries that make up the Standard Model in even more detail. This will include a deeper dive into the ideas of quantum electrodynamics, or QED, and quantum chromodynamics, or QCD, as well as the symmetries underpinning all these concepts. So let's move forward and dive into that next.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.